Hi, everyone. Having concluded our discussion of multivariate analysis with the discussion of the divergence theorem in the previous video, we will now turn our attention for the remainder of this course to building the Lebesgue theory of integration. In this video, we'll discuss a little bit of the history that leads to the transition from the Riemann integral to the Lebesgue integral, as well as begin to set some of the foundations for what will later become Lebesgue measure and Lebesgue integration. When we think about this in a historical context, there are roughly 250 years between Newton and Leibniz first thinking about derivatives and formalizing the notions of calculus to Lebesgue, who really starts to build this integral, which is in a sense a better type of integral. We'll discuss what better means a little later on, but a better type of integral than what, say, Riemann had previously been working with. So Lebesgue actually published this notion of what we'll eventually define as Lebesgue measure and the Lebesgue integral. He actually published this as part of his dissertation, his dissertation ends up getting published in a journal in 1902. I always like to bring this up because it's for the first time, maybe in your mathematical career, we're actually getting into 20th century mathematics. So there's a lot that happens right leading up to this. But we are now firmly in the 20th century, just barely, but we are in the 20th century, and we're going to discuss some 20th century mathematics here. So in it, he develops sort of two things, this idea of the measure of a set. Now, again, this isn't happening in isolation. There are lots of other mathematicians who are really thinking about formalizing what they call the content or the measure or the size of a set. And then this then turns into, once he has this measure of a set, defining an integral based on that measure. And again, that integral, there are lots of people thinking about things going on, particularly with respect to integrating series term by term. So mathematicians like Fourier and others, right, are really trying to understand, there's this whole trajectory where they're trying to understand the convergence of these series and whether these infinite series, whether you can integrate them term by term, all of those things. So it's from this sort of lineage, the convergence in some ways of these two mathematical ideas. I believe Borel was Lebesgue's Ph.D. advisor. I'll have to actually double check that, but I think that's right. So if you've heard of, we'll talk about Borel sets and a Borel sigma algebra. But there's these two lineages sort of converging here at this time that Lebesgue is working. So in developing this new integral, really Lebesgue's motivation was twofold, and there were these sort of two fundamental problems that were coming from the Riemann integral. Now, anytime you have some new mathematical object, so you sort of imagine, at some time, you have Riemann's integral, and for a while, you go, wow, this is great. Look at what I can do with this formal notion, and I can prove all these things, and so on and so forth. And so for a while, it's great. And then you start to realize that, well, okay, it's great for some things, but maybe it also has some deficiencies. So, over this period of time, right, folks are starting to discover some things that just maybe aren't ideal about Riemann's integral. So these two sort of fundamental problems, the first is essentially that there were functions for which the integral of the derivative doesn't recover the original function, and vice versa. Sometimes the derivative of the integral is not the original function. So there is a function in particular here. If you want to look up, this is sometimes referred to as the devil's staircase. This is one example of such a function. So, for example, this function hits every value between 0 and 1. However, its derivative is 0 at almost every point. And so when you try to integrate the derivative of this function, you get 0, but the function itself is not 0. So, this sort of, there were a lot of what was happening at this time. And actually, more broadly speaking, at this time, folks are really starting to try and sort of push at the limits of mathematics. Some of this results in a big push towards formalizing mathematics, sort of axiomatic formalization of mathematics. But out of this comes lots of these sort of horrible seeming counterexamples to things. The Devil's Staircase is one that you can pull it up on Wikipedia or wherever, and learn more about that. We may actually look at that a little later on, but for now, just again, there were some functions for which derivatives and integrals weren't sort of cooperating together the way we might hope. The other problem had to do with sequences of functions. And again, if you think about this, this is really related to the series of functions sort of problems that people were working on. The integral of the limit of a sequence of functions was not necessarily the limit of the integrals. So if you actually think back to Math 5610, we looked at a theorem that said if you have a sequence of functions which is converging uniformly, then the limit of the sequence of integrals of those functions is equal to the integral of the limit of those functions. But that required uniform convergence of those sequences of functions. However, we know there are other sequences of functions which don't converge uniformly, that say only converge pointwise, but still for which the limit of the sequence of integrals is equal to the integral of the limit of the functions. So the question sort of becomes, well, maybe the uniform continuity thing is not right? Maybe it's a sufficient condition to guarantee that, but not necessary. So maybe there's something wrong here too with the integral, right? Maybe we need to rethink how we're actually integrating these things. Now, again, how often do these really come into play in everyday life? Maybe not all that often, but theoretically, they are sort of important considerations that Lebesgue was hoping to try and address. So Lebesgue's goal, this is in his own words, it's a translation of his own words from the publication of his dissertation. So it thus seems to be natural to search for a definition of the integral, which makes integration the inverse operation of differentiation in as large a range as possible. And really, it's that last piece, in as large a range. We want to make integration be the inverse operation of differentiation for as many functions as we possibly can. Okay. Certainly for the Riemann integral, that worked for some functions, maybe even a lot in some sense, but Lebesgue's goal was really to expand this as far as possible. Again, we have these sort of two, you have Borel's research on the content of a set, you have Darboux, who's working on some more of this sort of integration specific stuff, and he's sort of Lebesgue is able to sort of merge these two together. All right, so, well, what did Lebesgue do? Well, it's going to take us most of the rest of the semester to really lay out what's going on here. But fundamentally, we can think of this as analogous to the Riemann integral, except for one important distinction. So if we think about taking the definite integral of some function, right? And here for both of these, actually, let me make this a little more pronounced here. So let's say this is our function. And we're also going to want to look at this function, but in Lebesgue's way. All right. So what's the idea of the Riemann integral? Well, the idea of the Riemann integral is you partition the domain of the function, right? So you come here and you say, okay, I choose some partition of my domain, right? And then I will use this to build rectangles, right? And yeah, I take a sample that tells me how high to make the rectangles. I'm not going to worry about writing that out, but let's just say I do something simple like a left-hand rule, right? If I just did a left-hand rule, then that would give me something that looks like this. And this is sort of my approximation of the area. And okay, then I look at I need to look at what happens as the norm of the partition goes to 0, things like this. But fundamentally, the idea is that you're approximating the area under the curve by these rectangles, which are made from partitioning the domain. And then you take some appropriate limiting operation to recover the true value of the Riemann integral. Lebesgue's idea, in some way, is to do exactly the same thing, but instead of partitioning the domain, to partition the range of the function over that set. So instead of looking at the interval AB, we're going to look at the interval in the range, which is, say, this whole interval right here. And this whole interval would be f of AB. These are just the values that my function hits, right, as x goes between A and B. So if I take this, now I can partition this, okay? So maybe I might partition it like this. And again, need not be, at least for the time being, need not be a uniform partition. Okay. So let's say I do like this, okay? And now I start building rectangles. Okay, well, it can't really do a left hand or right hand rule here, but I could do maybe sort of a top hand or a bottom hand rule here. So maybe I'll do it sort of from the top. So this would give me some sort of rectangle like this. This would give me some sort of rectangle like this. Okay. But now already I run into the first problem, which is that now I really have to sort of break this up into two rectangles, right? Like this under here, like my function breaks up, okay? And the same thing is going to happen when I go up here, right? If I'm just taking the top values, I'm actually only going to get this. Okay. Same thing when I come over here, I'm only going to get this. Now, so like this is okay, this is okay, this is okay. Here, though, something weird is sort of happening. Now, why is it happening? It's happening because my function is not one-to-one, okay? Which means that if I look at the preimage of this set, it is not necessarily just an interval, right? In this case, it's a union of two intervals. So when you think about what happens over here, right, over here, all of our rectangles, the base was just the partition of the interval, of the domain, right, that subinterval of the domain, and the height, right, was just the function evaluated as a point. And because it was a function, right, there was only one value above it. Now what's happening here is, okay, our base is some subinterval from partitioning our range. That's fine. But now the sort of, if you think of this as either the base or the height, okay, but whichever one, let's say we think of this as the height. The problem is the base is now going to be the preimage of this interval, right, which is not necessarily a set that has any nice structure. It's certainly not necessarily an interval, right? Now, as we've drawn it here, this sort of nice function, okay, it's a union of two intervals, not too bad, right? But if you think about a function like sine of 1 over x, like, and you include 0, right, that could be like an infinite union of intervals. Or what if you take a function that's not even continuous, right? Then it doesn't even need to be intervals, right? It could just be any old random set in R, right? So the first thing we realize is that if we want to, so this is fundamentally Lebesgue's idea, but in order to make sense of this, we have to be able to talk about sort of the length of sets in R, which are not necessarily intervals, right? Maybe they're unions of intervals, but they could be any sort of set in R. So the first thing we want to do is we need to make sense of what it means to talk about the measure. We're going to call it the measure, but you can think of it as an extension of the length, right? So what's the measure of some set in R? All this is doing is really saying if we want to flip the rectangles to talk about Lebesgue integration, in order to make sense of the bases, right, the length of the bases, we've got to be able to measure any set in R. Okay, or ideally, that's what we'd like to do. All right. Well, uh, if we're going to measure sets, what do we mean by that? What would we like a measure to do? So we want to measure. We're going to call this mu. We would like for it to be a function that assigns a size. Now, what property should I want size to have? Should probably be non-negative, right? Okay. So I'd really like a function mu that takes as an input a set and spits out a number between 0 and infinity, right? Including possibly 0, maybe including infinity. Okay. Ideally, mu would satisfy these four properties. Now, I want to note that this is not a definition. Okay. Right now, this is just a wish list. Okay. So what I like? Well, if I want to think of the measure as being sort of an extension of length to other types of sets, well, then I'd like the measure of an interval to just be its length, right? It'd be sort of silly if I define this measure and it was supposed to be an extension of the length of an interval, but for an interval, it didn't return its length, right? So that's the first thing I'd like. The measure, if I plug in an interval, it ought to give me back its length, right? And I can easily define the length of the interval AB is just B minus A, right? All right, so that's the first thing I'd like. The second thing I'd like is something that we're going to call translation invariance. And the idea here is if I have a set sitting here, any set, and I know its measure. Well, if I take that set and I just shift it to the right or shift it to the left, it ought to have the same measure, right? Shifting things around should not change the size of the set. So all this is saying is if I have a real number x and a set E, which is a subset of R, then the measure of the set X plus E should be the same as the measure of the set E. So shifting the set E by X should not change the measure. I should get the same measure regardless. We call this translation invariance. Now, the third property says, if I have a whole bunch of sets, En, so I have E1, E2, E3, E4, and they're disjoint. So if you take the intersection of any two, it's empty. They don't overlap at all. If I take all of these sets and I compute the measure of each of them and add them all together, that ought to be the same as unioning all those sets together and then taking the measure, right? Basically, the measure of all of these disjoint sets union together should be the sum of each of their individual measures, okay? Now, we're going to call this countable additivity, in part because we want it not just to work for finite collections of sets, but also for countably infinite collections of sets. Okay. And the last thing we would like, right, I'd like to be able to measure any subset of R that you give me, right? If you give me any subset of the real numbers, I'd like to be able to say, here's its measure, right? I can do that for intervals. You give me any interval, I can give you its length. I'd like to be able to do that for every subset of R. Now, this is a wish list, and much like you sometimes have to explain to children on Christmas, right? We don't necessarily get everything we asked Santa for. So whoever mathematical Santa is, he unfortunately does not give us everything on this list. In fact, the thing we're definitely not going to get is the last thing. Okay, it will actually turn out that not every subset of R is going to be able to be measured. Okay. 3 is a little trickier. We're actually going to weaken it a bit and then sort of come back to it. So we'll actually at some point weaken this to countable sub-additivity, and then we'll say, well, actually, for certain things, you do get countable additivity. Okay, so 4 we're not going to get. 3 we'll play around with a little bit more. 1 and 2 we will in fact get. Okay, so sort of like you got the first 2 things on the Christmas list, you sort of get the third. Maybe it's not quite the version you were looking for, but it's close enough. And then we're not going to get the 4th thing here. Well, as soon as I tell you we're not going to get the 4th thing, sort of the first question that you ought to ask is, well, then what subsets of R will we be able to measure, right? And it actually turns out that what we want to start by doing is we actually want to start by understanding sort of certain subsets of R and they will eventually help us build the set of subsets of R that we will be able to measure. Okay. So we're going to start by really jumping into some set theory. Okay. And if it's been a while, since it's a very different way of thinking than what we've been doing. So just, work through it. It'll be okay. We actually want to start by defining something that seemingly has nothing to do with analysis, right? That's because it really, in a way, is not about analysis, it's about set theory, but it will come in very handy for us. We want to define an algebra of sets. So if I have a non-empty collection A of sets, so I have this collection of sets, A, I'll call it an algebra if and only if the following two things hold. So first is the union of any two sets in A is also in A. And the second is that the complement of every set in A is also in A. So, for example, let's imagine you have so let X be a non-empty set. Okay. Oh, not two T's in set. What if I wanted to construct an algebra which contained X? Well, what would that need to have? Well, if I want the algebra to contain X, okay, certainly X has to be in there. And well, the complement of every set in A also has to be in A. So if X is in here, X complement has to be in here. Well, now I have two things, so I should maybe start worrying about unions. So now if X and X complement are both in here, then their union has to be in here. But what's the union of X and X complement? It's whatever the whole set is, whatever your universal set is. So I'm going to call that U, okay, for my universal set, right? So like if my universal set is the natural numbers, right? And let's say X is the set of even numbers, right? Then I have the even numbers, I have the complement, right, which would be the odd numbers. Right? Then I have the union of the even and the odd numbers, which is the whole set, the natural numbers, right? But then I have the complement of that, which is the empty set. Now, a couple things to note here, right? So the first thing I want to illustrate here is that if you have basically if you have if you have an algebra that contains any non-empty set, then it automatically must contain the universal set and the empty set, right? So pretty much every non-trivial algebra is going to contain the universal set and the empty set. Okay. The other thing I want to sort of point out and emphasize from this is that we define an algebra as being essentially a set of sets which is closed under union and complements. But because it's closed under union and complement, then it's also closed under intersection, right? So notice that right here, if I take X intersect X complement, I get the empty set, right? If I take the empty set intersect X, I get the empty set. If I take the universal set intersect X, I get X, right? If I take X complement intersect the universal set, I get X complement. So it's also all the intersections are contained in here. Okay. Now, this is fine. This is just defining sort of a collection of sets, right? And an algebra is just a particular collection of sets. that has these two nice properties that it's closed under union and intersection. And again, therefore it's closed under union and complement and therefore closed under intersection. I should also point out one of the reasons this follows from De Morgan's laws, right? So if let's say your set, your algebra contains two sets, capital A and capital B, well, then you can write the intersection of A and B as A complement union B complement complement. Okay. And if A and B are in your algebra, then A complement has to be in your algebra. B complement has to be in your algebra. The union of A complement and B complement then have to be in your algebra. And since this union is in your algebra, its complement has to be in your algebra. So you can, it's just an application of De Morgan's law to show that an algebra also has to be closed under intersection. All right. Now, it actually turns out we want even a little more structure than an algebra. Okay. Note here that the first condition, that the union of any two sets in A is also in A, that actually will extend. You can apply that any finite number of times, right? And sort of by induction, you can show that any finite union of sets also has to be in A. So if you have E1, E2, E3, all the way up to En, which are all sets in your algebra, then the union of the sets Ek from 1 up to N must be in your algebra. But it only works for finite unions. We want to extend this. So if we have an algebra of sets A is called a sigma algebra if, in addition, every union of a countable collection of sets from A is also in A. So you can think about extending this, right? Another way to say this is if En is a countable collection of sets with En in the algebra for all natural numbers n, then the union n equals 1 to infinity of the Ens also ought to be in the algebra. Okay. So the set of sigma algebras is a subset of all of the algebras, right? Every sigma algebra is an algebra, but not every algebra is a sigma algebra. Okay. Now, this is all sort of, I mean, it's fine definitionally. I think what's most helpful and what we'll sort of conclude this video with is working through a few examples of collections of sets and asking ourselves, are these algebras? Are these sigma algebras? And in particular, I think anytime we're looking at new definitions, examples and non-examples are equally as helpful in sort of building our intuition. Examples, help us see, okay, here's the kind of structure we generally expect. Non-examples help us understand, how these conditions can fail, right? How do you fail? How do you have a collection of sets which contains some countable collection of sets, but when you union them all together, the union is not in that collection, right? How does something fail to be a sigma algebra? All right, so let's start with the trivial example. I have a non-empty set X, and I just take the collection of sets, which is the empty set and the whole set. And I'm thinking here of that this set is like my universal set here, okay? So is this a sigma algebra? Or sorry, let's start with, is this an algebra? Okay. So the first question I need to ask myself is if I take the union of any two things in my algebra or in my collection, is it in here? So, well, there are only there are only really four possible unions: the empty set union the empty set, which is the empty set; X union X, which is just X; the empty set union X, which is just X; and then I guess there are really only three, right? Because union is symmetric. So, I mean, you could say X union the empty set, but that would also give you X. Okay. So it's certainly closed under unions. Okay. The next question I would ask is it closed under complements? Well, what's the complement of the empty set? Well, I'm thinking of X as my universal set, so the complement of the empty set is just X. What's X complement? Well, it's the empty set. Okay. So this is certainly an algebra. Okay. So it's an algebra. Okay. So again, this really just boils down to the fact that if I look at the empty set union X is X. The empty set union with itself is the empty set. X union with itself is X. And all of these things, right, X, the empty set X, they're all already in my collection. Okay. Similarly with complements, the empty set complement is X, and X complement is the empty set. Okay, so this is certainly an algebra. Now, the question, is it a sigma algebra, is almost vacuously true, because, I mean, how could you take countable intersections here? Well, you could reuse things, but it's not really going to change much. So you imagine you take, so you could take a countable union of empty sets, but those are all empty sets. In fact, you can basically throw away any empty sets you union on. So if you have something that only has a finite number of x's in it, so you have some, like, think about sigma algebra here. So imagine maybe you even have this like alternating thing. All right, well, let's say you do this. And then eventually it just becomes all empty sets. Okay. Well, you can throw away all those empty sets, right? You could just say this is the same as X union X. There are only two X's here, and that's X, and that's in A. Okay. So if you have some countable union, which contains only finitely many X's, then the fact that it's an algebra will give you that you're just going to get back X. So that's going to be in your set. If you have something that, say, contains infinitely many X's, right? Well, take however many X's you want. The union and a countable union of X's is just X, right? So even if you have a countable number of X's, X union, sorry, I guess the way I drew this makes it seem like this was ending. It's not. That this is a countable union. So if you just took and kept unioning X's, right, you just get X, right? So with these countable unions, if any one of the things in there is X, you get X back. The only way you don't get X back is if you union together a whole bunch of empty sets, right? So either way, you get the empty set or X, which is already in your collection. This collection is a sigma algebra. Okay. Again, it's not quite fair to say it's vacuously true, because you can have countable intersections, but they're countable intersections of finitely many distinct things, only two distinct things. And so it's really not, there's not that much that can happen. All right. Let's look at another example. Let's just take the power set of the natural numbers. Okay. So what's the power set of the natural numbers? Recall the power set of any set is just the collection of all subsets. So here we're looking at the collection of all subsets of n. Okay. I claim that the power set of the natural numbers is a sigma algebra. So if I just want to check if something is a sigma algebra, I don't really need to check that it works for finite. I mean, finite will usually sort of fall out of thinking about whether it would work for a countable collection of sets. Okay. So imagine I have E1, E2, E3, En, right? And n goes off to infinity. each of these is a subset of the natural numbers. And now I union them all together. What do I get? Well, they're all subsets of the natural numbers. When I union them together, I get some other subset of the natural numbers. And every subset of the natural numbers is in the power set. So any countable collection of subsets of the power set of n is also in the power set of n. Okay, so it is closed under countable unions. What about complements? Well, imagine I take all the even numbers, right? That's something that's in the power set of n. I take its complement, and I'm taking its complement over n here, right? N is my universal set. So what's its complement? It would just be the odd numbers, which again is just the natural numbers, right? So you can always come up with this complement, right? For any set you have, right? Its complement must also be a subset of the natural numbers. So it's also in the power set. Okay. So this one is in a way, it's a more complicated set. It has many more things than the trivial case, but because it contains all of the subsets of n, it's sort of automatically true because any two subsets of n, their union is a subset of n, and the complement of any subset of n is a subset of n. You get that the power set of n is a sigma algebra. All right. Let's look at one more example, and this one is going to be a little trickier. So let's sort of step through this, and we're going to step through this piece by piece. So let's think here first about the algebra part of it. Okay, so we're looking at what we're calling it the cofinite algebra. Okay, so I'm going to sort of giving away here that it is an algebra. Okay, so imagine I have some infinite set X. And now I'm going to define this script F to be the collection of all subsets S such that S is either finite or has finite complement. So it's all the subsets of an infinite set that are either those sets themselves are finite or their complements are finite. Okay, so not all of the things in F are necessarily finite, but if they're not finite, their complement must be finite. Okay, so this is called the cofinite algebra. Okay, so let's think about how I might prove this. So the first thing I want to show is that this is closed under unions, under finite unions. Okay. So let's take two sets. Let's call them A and B in this script F. Okay. Now, what can I say about A union B? Well, if A and B are both finite, so okay, A and B they're in this cofinite algebra. So either they're both finite, one of them is finite and the other has finite complement, or they both have finite complement. Okay, so if A and B are both finite, then A union B is finite. Right? If A has 10 elements and B has 4 million, then A union B has at most 4 million 10 elements. Right? However many elements A has and however many elements B has, the sum of those two is an upper bound for the elements of A union B. Of course, if they have elements in common, then that'll reduce the size of the union. Okay, but if A and B are both finite, then their union is finite. Okay, if A and B both have finite complement, well, then what's going to happen? So if A and B both have finite complement, then if I look at A union B complement, What is that? That's A complement intersect B complement. So that's De Morgan's law there. Okay. So A and B both have finite complement. That means that A complement is finite, B complement is finite. Their intersection is finite. So this is finite, which means that A union B has finite complement. So if A union B, in the first case, A and B are both finite, then A union B is finite. So A union B is in the cofinite algebra. If A and B both have finite complement, then A union B complement is finite. So A union B has finite complement and is in the cofinite algebra. Now, what if one of them is finite and the other is infinite? So I'm just going to do this in the case. So what if A complement and B are both finite? So the set A has finite complement and B is finite. Okay. Then let's check the union. So what can I say about A complement union B? Oh, sorry, I want to say something about A union B, right? A has finite complement, B has B is itself finite. So now I want to see what happens with A union B. A has finite complement, but itself, I don't actually know what's going on with A itself, right? It could be finite. Well, I guess if it has finite complement, then it's infinite. So this thing itself is infinite. What about its complement? So what if I try to look at the complement? So the complement would be A complement, which is finite, intersect B. Sorry, intersect B complement. Okay. But B is finite, which means B complement is infinite. Okay. But now notice here, this is okay because I have A complement, which is finite, and B complement, which is maybe infinite, but I'm intersecting it with a finite thing. So this is finite. Okay. So in any case, A and B, oh, it's a beta, not a B. A and B being in F implies A union B is in F. Now, the second part of this is actually pretty straightforward. I want to show it's closed under complement. And I can pretty quickly finish this up. So let A be in F. Okay. Well, then what does that mean? That means that A is either finite or has finite complement. Okay. If A is finite, then A complement has finite complement. Why? Well, what's the complement of A complement? A complement is just A. Okay. So if A is finite, then A complement has finite complement, so it's an F. If A has finite complement, then A complement is finite. Okay. So in either case, A being in the set F implies that A complement is in F. Okay. So this is in fact an algebra, right? And again, the name probably gave it away a little bit, but that's okay. So we've got certainly now that it is an algebra. The question then becomes, is it a sigma algebra? Now, as I alluded to at the beginning, sometimes it's helpful to have examples and non-examples. It's going to turn out here that this is not a sigma algebra. So if I want to show that this is not a sigma algebra, how do I do that? Well, it might be nice, right, to find a particular example, right, for which I have a collection of sets, each of which is in the cofinite algebra, but their, say, countable union is not. Okay. So pretty actually straightforward example here. And in fact, we're going to even specify. So we'll say F is not a sigma algebra. Okay. And let's take a very specific example. So let's take our infinite set here to be just the natural numbers. Okay. And let's note then, so if I take the set that just contains one single natural number, so the set that just contains k, this is certainly it's an element of the cofinite algebra. Why? Because it's finite. And this is a finite set, and this holds for each natural number k. So what if I just took then all of the even ones? Okay. So then if I took the union of, say, 2n, right, over the natural numbers, this just gives me the even numbers, right? Now, each of these is what? Each of these is in F, okay? Its union is just going to give me the even numbers, or I'll just write that as 2 times n, okay? Is this in F? Well, is this set finite? Well, no, right? Does it have finite complement? Well, what's the complement of the even numbers? It's just the odd numbers. So no. So this is not in F. So what do we have here? We have an example of, we take the sets which are just the individual even numbers. Each of those is in F because each of them is finite. It only has one thing in each of those sets. We take their countable union and we get something which is not in the cofinite algebra, right? So here, F cannot be a sigma algebra because I've explicitly shown that there is a particular countable collection of sets, each of which is in F, such that their countable union is not in F. And therefore, this cannot be a sigma algebra. Now, already we're seeing that this is probably the simplest example of something that's not a sigma algebra. So lots of nicely behaved things are sigma algebras. And in fact, in the next video, what we will do is actually we will define a very particular sigma algebra on the real numbers, right, that will eventually turn out to help us define, it would turn out that that is exactly the set of measurable subsets of the real numbers. Okay. So all of this work in thinking about sigma algebras, what it's really helping us to do is it's going to help us define which subsets of R are measurable and which ones are not. So in the next video, we will introduce those sets. Those are going to be called Borel sets, and we'll talk about the Borel sigma algebra. And we will then, once we have that, that will serve as essentially the domain of our measure. It will tell us what's on which sets we can actually compute a measure. So we'll begin all of that in the next video.